Welcome to the HyperX Academy. Today's tutorial is going to take a look at a case study involving a grid-stiffened rib. By the end of the tutorial, you will be able to use HyperX to properly size metal grid structures, work with panel segments, and size to a minimum buckling eigenvalue. For this case study, we will make use of the Grid-Stiffened plugin for sizing metallic grid structures and HyperFEA to size the stiffener segments. To begin this tutorial, we will first open the database and project located in your training folder as shown. Today, we will use the T1001 Stiffened Panels Machined Rib database and the Stiffened Panels Machine Ribbed project. Next, we will import the rib carve-out FEM located in the FEA folder of the training directory. Notice this FEM has both static and buckling subcases. We'll focus on the static case for now, so let's take a look at the design loads. Because the FEA was run at ultimate load, we will use a 0.67 limit factor for the static case. Next, let's create a structure. To create panel segments, all panels and beams should be in the same structure. Note, interface flanges are not to be sized, so there is no need to add them to the structure. Now, let's create panel segments. Panel segments are a special type of zone made of a discretely modeled stiffener and the skin panels connected to it. This allows HyperX to recognize the combination as an entire system rather than individual zones. Combining the two allows loads processing and sizing to be performed with respect to the segment rather than the individual components that make up the segment. To do so, navigate to the Structure tab of the ribbon and select Automatic Panel Segment Generator under Technique 2. Then, select all beam boundaries as shown. Next, let's review the panel segments. Click on any beam to highlight the entire panel segment, and then select Edit under the right-click menu. This will reveal which elements make up each panel segment entity. In the next step of this case study, let's set up our panel segments for sizing. First, let's assign design properties to both the skin and stringer segments. To do this, open your Design tab in the Property tree and drag the properties to the appropriate panel segments. Let's inspect the design properties and confirm we are using the same material for both. Notice, for the bars, this is a cruciform panel design property since these bars will be sized as part of a panel segment. Also, note that Technique 2 is indicated to show the bars are tied to the skins. The T-skin variable is grayed out because it is assumed to be inherited from the corresponding skins. Next, let's create and assign analysis properties. We want to analyze both strength and stability for each segment, so both of our properties will consist of failure modes made of methods from the Grid-Stiffened plugin package. To do so, first right-click on the Analysis tab in the Property tree and select Create Panel. In our case, let's label our property as Skins. Now, let's choose the failure mode labeled Grid-Stiffened from the list as shown. Once selected, let's label the failure mode as GS Skins. In this case study, let's use GS orthogrid buckling, GS von Mises element centroid yield, and von Mises element centroid ultimate. Make sure to change the drop-down for the yield criterion to limit so the analysis can be assessed accordingly. Then, select Apply and close out your window. Your analysis property will now be available in your property tree as shown. Next, let's create a property for our bars. To do so, again, right-click on the Analysis tab and select Create Beam and label your property as Bars. Then, we will select our two failure modes. First, let's add a stiffness failure mode. Once selected, label your failure mode as required stiffness bending and select stiffness bending from the criterion list and click apply. We'll use this later with HyperFEA. Then add a grid-stiffened failure mode for your ribs and change the label to ribs. Let's select crippling and bending, crippling axial only, plastic bending ultimate, and plastic bending yield. For plastic bending yield, remember to switch to a limit load. Next, click apply and confirm your new analysis properties have been created under the property tree. It should be noted that all grid-stiffened methods are documented in the published plugin section of our help system. Now, let's create and assign average load properties. To do so, right-click on Loads in the property tree and go to Loads FEA and select Create Average. Then, select Tension and Compression and click Apply. As always, check your property tree to confirm your loads were accurately created. Now, as your final check, navigate to your property tree and confirm your design, load, and analysis properties are assigned in the property tree as shown. Also notice, when you click on a property, the corresponding structure it's assigned to will highlight accordingly. Now, let's size and review the results. To do so, click on the structure tree node we want to size. Next, click the Size button as shown. Note, sizing is slower for panel segments because the algorithm is sizing each segment as a system, rather than as individual stringers and panels. Now that the sizing is finished, click the legend and review the results. Let's review some of the features of the Grid-Stiffened plugin. Let's say, for example, you wanted to account for a hole in one of your panels. The Grid-Stiffened buckling method will analytically account for a hole. The diameter of the hole should be defined in the failure mode. In this case, let's use a diameter of 2.5 inches. Let's take a look at a pocket with an already low margin of safety and see how incorporating a hole will impact it. First, let's take a snapshot of the margin of safety prior to the hole. Next, let's reanalyze the pocket with as-sized dimensions and review the result. To do this, run analysis for the pocket of interest, and notice the orthogrid buckling margin is now negative for this pocket. This is because the allowable buckling load has been knocked down to account for the hole. Next, let's implement machining tolerances. The Grid-Stiffened plugin methods can also write margin with respect to machining tolerances. The tolerance parameters are defined as user constants, and the table on the screen outlines the meaning of those different user constants. Next, let's update both the skin and bar failure modes to account for the tolerances as shown. Then, let's reanalyze the rib to account for the machining tolerances and review the results. Note, several pockets and ribs may pass margin criteria at nominal thickness, but fail once machining tolerance is taken into account. Use the data probe feature to compare the thickness values, and we will see the thinner plates are more affected by the thickness tolerances. Now, let's size zones with negative margins to account for the machining tolerances. To select each color bin containing negative values, hold Shift and select the desired color. This selects corresponding zones with negative margins and allows you to quickly resize. Notice how the zones that had negative margins have been resolved and resized with positive margins. Next, let's set up sizing for eigenvalue buckling. In our example, we want to implement a required first buckling mode eigenvalue of 1.0. We want to use HyperFEA to size only the rib zones, not the skin pockets, to meet this requirement. First, create a set containing only the rib zones by navigating to the Structure tab of the ribbon and clicking Set. Then, label your set as bars and select your stringer segments from the structure tree to include in your zone selection. Finally, click Create. Next, let's open HyperFEA and create a manual constraint. To do this, navigate to the Run tab of the ribbon and select HyperFEA. Then, click FEA Constraints and select the Manual Constraints option, and then define the manual constraint as shown. This manual constraint definition is telling HyperFEA, hey, let's meet the required eigenvalue target for the selected buckling load case by adjusting the D11 stiffness of the rib zones. Next, let's run HyperFEA iterations until EV criteria is met. Then, review the sizing results and notice how, in this case, it took 3 iterations with a Nastran buckling solution to meet our target eigenvalue. Also, notice that for each iteration, the weight of the structure is increasing. This is because stiffness is being added to the bars in order to chase out buckling modes that are lower than our target. To understand more on how that algorithm works, see our FEA Constraints help page, shown on the screen. As we look around, you will notice the controlling criteria of the D11 stiffness is controlling the height of the stiffeners. By turning on the deformed shape of the buckling subcase, you'll notice the stiffeners are tallest where there is the most deformation from the first real mode. Thanks for stopping by the HyperX Academy. We hope you enjoyed this case study, and we'll catch you in the next HyperX Academy tutorial.